Okay, thank you for the time. Uh, Let me introduce myself. My name is Putu Wijaya Sunu from Bali State Polytechnic, and I would like to deliver our research entitled Thermal Performance of Hot Water System Produced by Air Conditioning coupled with Heat Recovery. Okay, I will start my presentation with this perspective Indonesian government policy, especially for energy conservation. The Indonesian government released the Peraturan Pemerintah Nomor 70 uh, tahun 2009 about energy conservation. Okay, um, let's start with waste heat recovery. The waste heat recovery can give a benefit to improve life cycle costs, such as lowering operating costs due to higher efficiency. The peak demand for domestic water heating can be reduced up to 95%, and co-production using a single space can reduce space, initial cost, and maintenance. In energy conservation perspective, the waste heat recovery can save energy, and superheat recovery can improve the COP. And last, for the in, environmental friendly, we can see the waste heat recovery that improve cooling capacity, thermal pollution reduced by again for recovering heat rejection from the condenser, and CO2 emission reduction. So our experimental setup, you can see in the right figure and the left figure. The aim of the research is revealing the performance of heat recovery unit equipped by a number of twisted. The experimental test rig, compression outdoor and indoor, a cell and coil heat exchanger, and water centrifugal pump. The nominal of evaporator cooling capacity is about 9,000 BTU per hour, and the power of compressor consumption of 0.75 kilowatt. The refrigerant at 22 used as a working fluid, and direct expansion evaporator as an indoor unit, compression copper tube, and aluminum fin. Meanwhile, the outdoor units include a capillary tube, a tube and fin, air-cooled condenser, and of course, the hermetic rotary compressor. Let's see the result of our experiment. Um, in this figure, we can see the effect of the number of twist tip. We use 1, 2, 3, and 4 twist tip in the head recovery unit. And from this figure, we can see that the head recovery equipped with twist tip, with a number of twist tip, has a temperature higher than the heat recovery without twist tip. Why? Now, of course, because the twist tip uh, induce the momentum transfer increase, and the turbulence for the flow in the flow will increase. So the heat transfer in the heat recovery unit also increase. In this slide, we can see the total energy absorbed by the heat recovery in the presence of the twist step. For the heat recovery system without twist step, the fluid flow inside the heat recovery, flowing from the bottom region to the upper region without disturbance, and the fluid flow in a smooth line, relatively constant velocity to the discharge section. Meanwhile, in the heat recovery with the twist tip, the fluid flow from the bottom region to the upper region, from the downstream to the upstream, starting the disturbance with the presence of the twist tip. The twist tip induces the flow condition inside the heat recovery unit. They increase turbulence strength, recirculation regions, and of course the fluid momentum. It is noted that the heat recovery equipped by four twister has the highest energy absorbed. The explanation why the energy absorbed by twisting heat recovery is the same way with the temperature phenomena. Okay, let's continue so we can take a conclusion of our research. The first, it is possible to apply the proper system to the increasing the temperature of heat recovery. And the second, based on the constant operation condition, the average heat absorbed uh, 0.56, 0.59, 0.59, and 0.65 kilowatt for the modified heat recovery. Okay, that's all our presentation. Thank you very much.